Hello, my name is Selenium, SE for short, and I am here to talk to you today about both real and ideal gases. So what do you think of when you hear the word gas? Maybe you think of oxygen, or the gaseous state of steam, or maybe you think of whoever smelt it dealt it. Well, you're not completely wrong, but let's talk specifically about ideal gases. Ideal gases have particles that move incredibly fast and randomly, which looks a little something like this. This is part of what is known as the kinetic molecular theory. Some other things that you should know about this theory is that the gas particles exert a volume of 0, or just about. And they can be at many different temperatures, but whatever temperature they are at, it is a representation of their kinetic energy. In many cases, there are a lot of particles in a given space, and all of them moving quickly around each other causes what is known as collisions. I'll show you what that looks like. Just because a gas is ideal does not mean that actual gases happen to behave like that. We can get real gases to behave like ideal gases if we have them at a very high temperature and a very low pressure. We'll get more into that in a bit. First, let's compare the formulas of both real and ideal gases. We will start with real gases. Okay, so you're seeing the formula for a real gas situation. So this V1 right here, that is the initial volume, pressure, the first or initial, number of moles, temperature. And then you have the final or the second situation of both volume, pressure, number of moles, and temperature. Let's compare this to ideal gases. Boom! So here is the formula for ideal gases, which can be manipulated in many ways, and you'll see how. So we have pressure times volume equals number of moles times R, which is set at a given value, you will learn more about that in a bit, times temperature. This is for ideal gases. So now that you know what the formulas look like, let's learn more about the characteristics of the formulas, being pressure, volume, temperature, number of moles, and R. You will also see how the formulas are manipulated. So let's meet our first characteristic, pressure. What's up? I'm pressure, also known as P in the equation for both real and ideal gases, because I'm kind of everywhere. Currently, as I'm sitting down talking to you, I'm putting the pressure of my body weight onto this couch. Technically, on Google, because you can find me on Google, I am the continuous physical force exerted on or against an object by something it is in contact with. In ideal gases, I'm going to show you what I am in that formula. So if you look here, I am equal to nRT over V. And you'll get to meet all of these lovely people in a bit. But for now, why don't we talk a little more about me? Not you, me. Not to toot my own horn or anything, but I am pretty much everywhere. I'm in ideal gases, real gases. I'm even in social situations like high school teenagers offering cigarettes to other high school teenagers and peer pressuring them to do so. But that is another story. Let's talk about all of me, not the song, and part of me. So, all of me, total pressure, can be found by this equation. So what you are seeing right here is all of me, or the total of me. So, all of me equals one of me, plus another one of me, plus another one of me, depending on the situation and varying from gas to gas. So, how do we find partial me? Well, we'll look at that equation right here. So, you'll see that part of me, so we'll say my arm, is equal to the moles of gas A divided by the total moles times all of me. So not just my arm, but that is how you would find part of me, or my arm, or maybe like my leg, or like my nose, or something of that matter. So let's talk about the units that I'm in. So what we just talked about was known as Dalton's Law because Sir Dalton decided to explore the importance of pressure in gaseous situations. So, as for the units I'm in, you can commonly find me in 3. Those being torr, ATM, short for atmosphere, and kPa. So, yeah, that's it. Okay, thank you, pressure. Now that we know who the P in the equations are, let's meet the rest, the N, R, T, and V, starting with N. Salutations. I am N, also known as the number of moles. No, not those kinds of moles. Moles, like a unit of measurement that can be found in many different places, such as the periodic table, or when converting grams of one element to grams of another element. You can also see me as the coefficients in many chemical equations. Howdy y'all, I am T, also known as temperature. If you haven't heard of me before, I am pretty much how much heat is present in a given situation. I can be in degrees Fahrenheit and degrees Celsius, but if you're talking about gases, I'm likely in kelvins. If you happen to live in the Midwest and you recently experienced some snow in April, you may not be the happiest with me at the moment, so I'll best be on my way. Is this mic on? Yes? Okay. Hello, I am volume. You've seen me in both real and ideal gases, as well as possibly in your geometry class at some point in time. But in terms of ideal gases, I am equal to number of moles times R times T, and that whole value divided by P, as you can see. Aside from being a button on your TV remote, I am pretty much how much space something takes up, and you can usually find me in liters, but occasionally I will be in milliliters. What's up guys, I'm R. All you really need to know about me is that I'm equal to 0.0821, get ready for this unit here, liters times atmospheres divided by moles times kelvins. I'll show you what that looks like. It looks like this. So I am equal to 0.0821 liters, so volume, times atmosphere, so pressure, divided by moles, so N, times kelvins, a unit of temperature, so T. So everyone you just met, they're pretty much all in my unit, but I'm only in ideal gases, so unlike them, you can't really find me anywhere but ideal gases. But yes, this is me, this is what I equal, and that is where I'm found. So now that we know what all the letters in the equations represent, let's talk about how they interact with each other. We will first talk about the relationship between temperature and volume. As temperature goes up, meaning it gets hotter, yee-haw, volume will go up as well. Hooray! This is a proportional relationship, meaning as one does one thing, the other does the same thing. But to test and study this relationship, we have to make sure that pressure is constant. Yep, don't mind me, I'm constant in this relationship. This happens because of a law known as Charles' law. The higher the temperature goes, the faster the gas particles are moving around, which means they're going to hit the walls of the container faster, therefore expanding the volume or the space that something takes up. And the less space that something has, the slower the particles are going to move, which means that the temperature will go down because of that. Oh yeah, volume and I are super duper close. When I'm up, she's up, and when she's up, I'm up too. Yes, it's true. Temperature and I have a proportional relationship, but to be fair, she's kind of friends with everyone. Now, let's talk about the relationship between pressure and volume. This is known as Boyle's law. Meh. Volume is overrated. I've met better. It's quite difficult getting along with pressure. We pretty much never agree. When studying this relationship between pressure and volume, we have to make sure that temperature remains constant. Yup, I'm constant in their relationship. When there is less volume, the gas particles hitting the outside of the container will hit with more force and therefore expand the volume of the given space. Kind of think like a balloon. On the other hand, if there is more space, then the rapidly moving particles have more time before they hit the outside walls of the container, meaning that they will hit with less force and therefore the volume will decrease. Think about it a little bit like this. If you were running around very quickly in random directions in a big room and a small room, you're more likely to hit the walls of the small room harder and with more force and likely hurt yourself more in the process than you are in the big room. Okay, now let's talk about the relationship between pressure and temperature. This is known as Lusick's law. When pressure increases, so does temperature. I can tolerate temperature, but if you ask me, she's kind of ditzy. In this situation and relationship, we must assume that volume is constant. Yes, in that relationship, I'm considered constant. This is because when the temperature goes up and it gets hotter, the gas particles start to move around even faster. As a result of that, they hit the walls of the container with more force, meaning more pressure, meaning pressure goes up. On the flip side, when it gets colder and the temperature goes down, the gas particles start to move even slower, which means that when they hit the walls of the container, they're hitting it with less force, which means that the pressure will go down. Hey, what about me? Oh yeah, and when studying these relationships, we have to make sure that the number of moles also remains constant the entire time. Thank you. Yes, I'm there the whole time. I'm just constant. I'm just constant when studying those relationships. So great. There you go. Well, that's all, folks. Thanks for hanging out with me, Selenium, as I talk to you about ideal and real gases, their formulas, and the relationships between pressure, volume, and temperature. Actually, that is not all. Hey, it's Kari here. I just wanted to thank you so much for watching this kind of lengthy video. Mrs. Desai, I truly appreciate it. I hope I did you proud. I hope you enjoyed my awkwardness and my plethora of colored sweaters. I know it was kind of a bit all over the place, but I hope I got the general message across well. And you'll notice that I have shared the original script with you. I will attach that in the Dropbox as well, but just in case, it is shared with you. And that includes everything from the stage directions to this very statement that I'm saying. So if there's anything that I may have left out or anything is confusing, it is likely in there. If not, I'd be more than happy to clear anything up. But I will see you in class. Thank you so much and have a great day.